button and start. And so to start the talk, I will just go over just a few minutes, take time to go over our group and what it does. So let me share the screen first. So can everybody see the screen? It says Delaware Valley Mass Spec Discussion Group.
Yes.
Yes, no? Yes, okay. So welcome everybody. Welcome to the Delaware Valley Mass Spec Discussion Group. So this is our landing page of our website, and I just want to go through and thank first our sponsors for this event. And this just gives you who we are. So we are a group of people who are trying to promote mass spec in the local communities and invite interesting speakers to our events and educate the public in general, schools and young mass spectrometrists who are just trying to decide whether they should be in mass spectrometry generally. So that's one of the goals of our group. So we have Jean Cisimero, who's current chair. And we have some new additions to this group. First, we have our chair-elect, Rachel, COT. I'm pronouncing it correctly, Jean. Is that correct pronunciation? Mm-hmm. Okay.
Yeah.
Technologies.
Yeah.
Brett Peterson is our secretary, and our past chair is Joe Cannon. We have a new treasurer, Key, from Agilent Technologies. And award chair remains the same, Steve Lamanaka from DuPont. I think he changed companies. We have to update that here. And Will Shen is our webmaster, and he's currently working for Waters. And I generally advise the group on activities. And before I announce today's speaker, I'd like to first also thank our sponsors. We have Mobile Iron, Agilent Technologies, Bruker, Gentech, IronSense, Joel, Keystone, LECO, New Objectives, NEMS, which stands for Northeastern Mass Specs, PST, Phoenix, S&T, Restec, AB Sachs, Shimadzu, Adapters, Thermo Fisher Scientific, Trajan, and Waters. So we thank you for your support, and we also thank you for your continued support for future events. So in addition to that, I would like to also share that we also have a social media presence. So we have a LinkedIn page, and also we have LinkedIn, Instagram, which shows some of our events when we are in person. And then we have a YouTube page, which will have videos that we record, and we will play them. We will post them once we get our speakers agreed to us posting them. We will put them here in this YouTube channel so that you can go and watch them at any time. So with those introductions, I would like to, let's see. I'm really thankful for Tom Rizzo, who's our speaker today, for accepting this invite. When I first invited him, I actually just give an introduction of how I got to know Tom. I was at ASMS a couple of years ago. He came up to my poster, and we had a nice conversation about what I was doing, and I got to know what he was doing. I already knew what he was doing, but this was a nice way to get acquainted and then also see how we could potentially collaborate. And we, of course, did manage to find ways to work in some capacity, and I hope we can continue that moving forward. But so Tom is actually from the US, although he lives and works in Switzerland. So that was a surprise to me. Tom was born in Queens, New York in 1956. He studied chemistry at RPI, or Rensselaer Polytechnic Institute, where he graduated cum laude in 1978. He then pursued his doctoral studies in physical chemistry at the University of Wisconsin-Madison and received his PhD in 1983. From 1984 to 86, he did a postdoctoral work at the James Franck Institute of the University of Chicago. And in 1986, he was named Assistant Professor of Chemistry at the University of Rochester. He was then promoted to Associate Professor in 92, within a year, and then full professor in 93. So that was a quick rise to in the ranks. And in 94, he then accepted a position in chemistry at EPFL, and his early research focused on the fundamental studies of vibrational energy redistribution in gas phase molecules using laser spectroscopic techniques. More recently, he has been combining laser spectroscopy, ion mobility, and mass spectrometry for applications in biomedical analysis. Some recent distinctions for his work include the Book Award of the Faraday Society in 2009, the Ron Heitz Award from the American Society for Mass Spectrometry in 2017, and the ERC Advanced Grant for his work in biomolecular analysis in 2018, and at the ACS Measurement Sciences Lectureship Award in 2022. He was elected Fellow of the American Physical Society in 1998, and also Fellow of the American Association for the Advancement of Sciences in 2011. He also won the teaching awards both at the University of Rochester in 92 and at EPFL in 2021. During his time at EPLF, Tom has served as the head of the Department of Chemistry from 1997 to 2004, and the Dean of the School of Basic Sciences from 2004 until 2017. That's a long tenure. And he has recently become a co-founder on a startup called IsoSpec Analytics, which combines cryo-infrared spectroscopy with mass spectrometry for biomedical analysis. So I'm really looking forward to Tom's talk, which is titled, Can Vibrational Spectroscopy Finally Find Its Place in the World of Analytical Mass Spectrometry? With that, please take it away, Tom.
Okay, I think, do you have to stop sharing? Yeah, there we go. And let me see if I could share. Let's see. Here we go. Okay. Does everyone see that okay?
Yeah. If you don't mind
Okay.
putting it on presenter mode.
It is in presenter mode. Or are you, oh, maybe you're seeing the wrong screen.
Yep.
Okay. Let me stop sharing and try it again. Let's see. Should have. No, you're not, you're still seeing it in presenter mode?
I still see the slides. If you can duplicate screens, maybe you might be able to.
Yeah, I might have to. Yeah, I have multiple screens, which is a problem. Hold
So
on
in
a
Zoom,
sec.
you can actually go and say duplicate screen, which will.
Yeah, I'll share the screen instead of sharing the app, and then it should work. But let me then do something a little different. Okay.
Yep, we see it now.
Now you see it. Okay.
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 For a moment. Okay, now we see it.
Now you see it. Okay, good. All right. Well, thank you very much for inviting me, Harsha. It's really a pleasure to talk to you. You know, since this is a not so large a group, if you want to be a little more informal and just stop and interrupt and ask questions along the way, feel free to do that. Otherwise, we'll have Q&A at the end. But let's keep this, you know, let's keep this a discussion group if we can. So, you know, I posed the title of my talk as a question. And why do I pose it as a question? Well, vibrational spectroscopy of ions inside mass spectrometers has been around for quite a long time, since the time of Bob Dunbar and Jack Beecham in the late 70s. In fact, they were doing infrared spectroscopy inside mass spectrometers. But still today, there is no commercial application of infrared spectroscopy in analytical mass spectrometry. And the question is, why not? And there are a couple of reasons, I think. The first is the speed at which one can measure an infrared spectrum. You know, when you combine ion mobility with mass spectrometry. The timescales are reasonably compatible, depending upon what flavor of ion mobility. You might have arrival times anywhere between 5 and 500 milliseconds, and that's fast enough that it couples with like time of flight mass spec pretty well. But the question is, how long does it take to measure an infrared spectrum? Now, a number of years ago, probably about 7 or 8 years ago, I was at ASMS, and I went to one of the hospitality suites and was speaking to the representatives from one of the big instrument manufacturers. And they asked me, I was telling them about what we were doing. At the time, the technology we were using was quite a bit different than it is now. And they said, well, how long does it take you to measure a spectrum? And I said, well, about 20 to 30 minutes. And they laughed at me and they walked away. They were no longer interested. Now, if I told them today that we could make that measurement on the order of 10 seconds, they might not have laughed and taken me a little. They might have taken me a little more seriously. So I think the speed traditionally has been a big barrier, but as I'll demonstrate to you today, that I think that's no longer a barrier. The second one is the complexity of measuring infrared spectra. The kinds of lasers that people have traditionally used look something like this. They were neodymium YAG pumped optical parametric oscillators, and they're kind of messy things. You need to be a bit of a laser expert to tweak these things and to get them to run right. And you'd never find this in an analytical laboratory. But today, one could use simple fiber pumped solid state lasers that are no larger than a shoebox, and you could put them inside a mass spectrometry box, and you never even know that you have a laser there. It's actually probably simpler than a MALDI laser. The third thing, I think, which has been an impediment is theory, the limitations of theory. Now, when one gets to a molecule any bigger than, let's say, a disaccharide, the spectra become pretty complex. And particularly because of the hydrogen bonding interactions within a molecule, which affects its conformation, it's really difficult to calculate those things accurately for anything, a disaccharide or larger, for example. But so that was, if you're trying to find the three-dimensional structure of the molecule, then that can be a problem. But if you're trying to do it for analytics and you just want to know what the molecule is, then a complex infrared spectrum can be a powerful identifying fingerprint. The infrared spectrum is really highly sensitive to the structural details of the molecule. All these hydrogen bonding interactions give very distinctive infrared absorptions, and it provides an intrinsic fingerprint of the molecule that one could use as a database. And if you think about the other databases that one uses, whether it be collision cross sections or retention times or fragmentation patterns, these all depend in one way or another on the experimental parameters. The temperature or pressure you have to control accurately in ion mobility, the collision energy and fragmentation, retention times one always has to calibrate for a particular column. Whereas an infrared fingerprint of a molecule is an intrinsic property of the molecule. If you measure it, in Switzerland or in New Jersey or in California, it's the same infrared fingerprint. And so it's a really robust identifier for a molecule. So with that introduction, let me tell you a little bit about what we do, about our experimental approach, and then I'll give you some examples of how we do it. So this is a schematic of our machine. We have an electric spray ion source. We then send molecules through an ion mobility device. At the moment, we're using a SLIM IMS, but this could be any flavor of ion mobility. And in fact, it doesn't even have to be ion mobility. As I'll show you later in the talk, one can simply use liquid chromatography. But we need something to separate molecules. And then we, so in our case, we get an arrival time distribution, which allows us to separate isomeric species, for example. We then pass those molecules into a cryogenic ion trap where we cool them, and that's where we do our infrared spectroscopy. And the kind of infrared spectroscopy we do is called messenger tagging spectroscopy. What we do is, as we cool the molecule in collisions with helium, we seed in a little bit of nitrogen, and we tag the molecules with a weakly bound nitrogen. And so what we're looking at is the spectrum of the nitrogen tag species, and we could demonstrate that the infrared spectrum of those species is not very different from the bare molecule. But in fact, that doesn't really matter because we're looking for a fingerprint of the molecule. And so if we're always looking at fingerprints of the nitrogen tag species, and that's what's in our database, that's fine. As we then shine an infrared laser on the molecule, when it absorbs infrared light, the energy will redistribute among the different vibrational modes and eventually knock off this weakly bound tag and produce a bare ion. And so what we monitor then in our time of flight mass spectrometer is basically the ratio of the tagged to untagged species as a function of the laser frequency. And so what we then get is, for these mobility separated species, for each one, we get an infrared fingerprint, which is absolutely characteristic of that molecule. And as I'll show you, we can do this for really quite complex molecules and still get very distinct infrared spectra. And part of the key to that is that we're actually measuring them at cryogenic temperatures. And so that simplifies the spectrum enormously compared to room temperature. So what I'd like to do is to show you our application first to the analysis of glycans. And well, why glycans? Partly because they are a nightmare of isomeric complexity. And there are different levels of isomeric complexity. The monosaccharide building blocks are isomers of one another. For example, glucose and galactose only differ by the orientation of a single hydroxyl on an asymmetric carbon. Similarly, between glucose and mannose. But then when you start to make glycosidic bonds to form oligosaccharides, since that bond is made at an asymmetric carbon, one could have beta or alpha configurations giving rise to different anomers. But because there are many different OH sites in which you can make those glycosidic bonds, you can have different regioisomers, this case a 1,4, beta 1,4 versus a beta 1,3. And because you can have multiple attachment points between sugars, you can have different structural isomers, linear or branch species. So from an isomer point of view, glycans have to be the absolute worst, right? There are just so many different possibilities of molecules that will have the same mass. So let's see what we can learn, what we can do with infrared spectroscopy. So here I'm showing a mixture of just two disaccharides, GalNAc-Gal and GluTNAc-Gal. These molecules only differ by the orientation of a single OH on this non-reducing end of the sugar. And when we separate them by ion mobility, using our SLIM device with a 13-meter path length, which is 7 cycles on this particular device that we used, and in this case, we see 4 different peaks. Now, at first we wondered why 4 peaks, since we only have 2 different isomers. Maybe they're different conformers of each other, but it turns out what we didn't realize at first was, because we have a free reducing end here, you will have both the alpha and beta atomers at the free reducing end on this carbon. And so you would expect there to be 2 species for each isomer, and that being the alpha and beta atomers at the reducing end. And in fact, that is what these 4 peaks correspond to. Now, if we then separately put these into our cryogenic trap, we can measure an infrared spectrum shown in gray for this particular case, and then we could compare them to a database spectrum that we measured by taking the individual species and measuring them. And you can see several things. One is that the spectra are really quite distinct. These two and these two just differ by the orientation of the anomeric OH at the reducing end. And you can see, while the spectra have similarities, they're easily distinguishable from one another. But you could also see how well they agree with our database spectrum. There's no way that we would misassign these. And so, these are the two anomers of the gal-nat-gal, and these are of the glut-gal. And it just shows you how good an infrared fingerprint is and how well it can identify a particular species. As I'll show you later in the talk, we could actually measure these spectra in a multiplexed way. So we measure all four spectra at the same time. Well, how about if we go to larger oligosaccharides? Here's some isomeric human milk pentasaccharides. They differ by the placement of the fucose and of the orientation of this last glycosidic bond. And you can see that each of them, while there are many different peaks, they're really very distinct from one another, and they form a really distinctive identifying fingerprint of the molecule. And so if we have it in a sample, we measure the spectrum, we can easily tell the difference between these different isomeric species. And then just to push it a little further, here we have some N-glycans. This is G1F, and so there are two isomers of G1F depending upon where this galactose sits on the non-reducing end. We've separated these in our ion mobility device using 60 meters of drift length, and you can see we could almost fully separate the four. And even for these quite large molecules, you can see they have very distinctive infrared spectra. And these spectra really provide good identifying fingerprints of these molecules. I think we've gone up to something like 12 or 13.
Tom, can I ask a question, if you don't mind?
Yeah.
I was curious to know what the four were here, 1, 2, 3, and 4. You said positional isomers. Can you point out?
So this is another case that where we have a free reducing end. So we have alpha and beta anomers of the two positional isomers. So that's why we have 4. Yeah.
Sounds good. Thank you.
So I think so. We could assign these two to the alpha and beta of the alpha 1,6 branch, where the galactose is on the alpha 1,6 branch, and these two down here where it's on the alpha 1,3 branch. And I think we've gone up to something like glycans with 12 or 13 residues so far, and still see quite distinctive infrared spectra. Now, everything I've talked about so far assumes that we have a database, and we can put these in a database, and that requires that we have standards. And glycan standards are not so easy to come by, particularly when one has to synthesize, if one has to synthesize them with a specific stereochemistry. And so what happens when we don't have something in our database? How do we identify an unknown species? And so we've developed a method to do that. And the way we do that is using fragmentation. So what we've designed is, this is a slim board in which we've engineered a series of different traps on the board where we can divert ions into these traps. And on one of these traps, we've put a pair of grids in which they're 0.8 millimeters apart, and we put a few hundred volts across them, so that if we divert ions into this trap, as soon as they go through these grids, they're accelerated. The pressure in here is about 2 millibar, and so you have energetic collisions which then fragment the ions but leave them in the trap. And so it looks something like this. we can take two species, for example, and we can separate them, trap one of them. As soon as it goes through the grids, they'll fragment, and we trap those fragments. But then we can recycle the fragments and separate them by ion mobility, put them into our cryogenic trap and measure the spectra of those fragments. And so let me give you an example as applied to human milk oligosaccharides. So here's a mass spectrum of human milk. No separation here. It's just, we've just done some liquid extraction, no liquid chromatography, nothing is labeled. And let's just focus on this M to Z 1241 ion. Because of its mass and because of what we know about human milk, we know it has 4 hexoses, 1 fucose and 1 glucnac, 2 glucnacs, I'm sorry. But we don't have no idea what isomer it corresponds to. So we can use high resolution ion mobility, and we see for this single mass a range of different isomers. So let's just take one of them, and I'll just walk you through how we identify that particular isomer. So let's take this one. We can take this, we can put it in one of our traps and fragment it, and then we can look at the individual fragments. And so here's the CID mass spectrum of this 1241 peak. And I'll first focus on the 876 fragment. We can separate that by ion mobility, and we see 2 features. We can measure the infrared spectrum of each of those features separately, or we can do it at the same time, as I'll show you in a few moments. And we then look in our database and see if there's a match. And in fact, in this case, we looked in our database, we find a match, and we can show that this particular 876 fragment corresponds to this particular oligosaccharide, the alpha and the beta anomers at the reducing end. And you can see the quality of the comparison between the fragment spectra and our database. And so we've identified that one. Let's just put this on the side. And now let's look at the 1095 fragment. There, we only see a single peak in the mobility arrival time distribution, but we can measure an infrared spectrum, and we get a match there as well, which tells us that we have this species. And in this case, we don't resolve the alpha and beta reducing end anomers. And we then, knowing that these are the 2 fragments, if we put these together, we know that mass to charge 1241 had to be this particular species. So this just gives you an idea of how we can break things down to the point where we have fragments in our database, and then we can assign the spectrum of the parent. Now, once we've assigned the spectrum of the parent like this, we never have to go through this procedure again, because we measure the infrared spectrum of the parent molecule, and the next time we see the parent molecule, next time we see that mass, we measure the infrared spectrum, and if it is this particular isomer, we can identify it because we've put that infrared spectrum in our database. And so we can grow these databases from fragments to larger and larger species, and identify these complex species, only having to go through this fragmentation process once.
Tom, hello.
Yes.
Steve Cohen here. Sorry to interrupt you, but I have a question.
Sure.
Is the 3, I guess, the infrared spectra are dependent on 3-dimensional structure. Is that right? Is that a
Yeah.
is that sort of correct? Yep. I mean, the hydrogen bonding, et cetera. I mean, whatever.
Yes.
Whatever other kind of bonding there is there. I mean,
Yep.
And so how much is it understood that, let's say, one given structure, your M over Z 1241 has unique, every single 1241 molecule will have identical 3D structure?
so two things. One is that we always anneal our samples, so we treat them fairly roughly. The SLIM itself does that, right? And we never see any change in the arrival time distribution as we do that, right? So we're purposely trying to anneal any conformer distribution. Now, one thing I didn't say is that we're looking at sodiated species here, right? We have not seen, we do this on peptides all the time, and we can see different conformer populations of peptides, and if you anneal them a certain way, you can change the conformer populations, but we haven't seen this with glycans. Now, the 1241, there are many 1241 isomers, right? So this is the arrival time distribution of the 1241 parent. And so there are many different isomers, and I am just identifying this one, but I would contend that these are not different 3D conformers, that they're likely to be different isomers, actually. I suppose all we can do really is see if we can change their populations. I can't definitively say that they're not different conformations.
Yeah.
But if the arrival time distribution doesn't change, it's probably a pretty good assumption, I would guess.
Yeah. Okay. Thank you.
Tom, I got a question to follow up on that. So you move into these other peaks as isomers, not conformers. So is that evidence from the IR spectros, the fingerprint that you get? If there were different conformers, you would see differences in the fingerprint. Is that how you?
Absolutely.
Yeah.
So I don't have it here, but if we but if I were to show you infrared spectra of these different ones, they will all be different. Absolutely, they have to be different, right? Yeah. Because they have different arrival time distributions, right? Which means they have different shapes. They will. I mean, there's no way that two things that are different enough to have a different arrival time distribution would have the same infrared spectrum. Yeah. In fact, it's much more, I think an infrared spectrum is one of the most sensitive measures of the precise conformation of a molecule.
Mm-hmm.
All right.
I didn't catch this in your, in your IR scan. What's the time scale compared to the drift separation?
The time scale of measuring the spectrum.
Yeah.
Okay, I'll get to that right now, actually.
Okay.
So, so the question is, I talked about timescales right at the start, and the question is, how fast can we do it? And let me show you a few details of our ion trap, and so this is what our cryogenic ion trap looks like. It's actually made out of a sandwich of PC boards. It actually looks like SLIM, but it's not. So we have RF stripes that can find the ions in this dimension, but we have, these are just DC pads. There's no traveling wave on here. We can address every row of DC pads separately, and so in this particular trap, we'll have a gradient along the length of the trap that looks something like this, right? So we can actually fill this trap. We can fill this trap, and we can manipulate these individual DC electrodes to block, and we can do that in time. We can control those in time. We can use this as a single trap, or we can make it into 4 or 5 different traps, or even 10 different traps, and we can manipulate that from outside the machine. We don't have to rewire anything. And so in this case, let's say now we've separated 3 different isomers of the same mass, and we want to measure the spectrum of those. We can do it simultaneously. So we pulse our cooling gas and our tagging gas into our trap, and this trap is cooled to about 40 degrees Kelvin. And then we can load these things into our trap, but we can put the blocking electrodes up so that we can separate each mobility separated species into a different compartment of the trap. we then can shine our laser through here, and if the particular molecule absorbs the infrared, it will knock off one of the tag molecules. And then we could sequentially read these things out really quite fast, and we get basically a mass spectrum of each of these species. And basically what you're seeing here is you're seeing the untagged species and the tagged species. That's actually a doubly tagged species. Sometimes we get that. And so we would then measure the ratio of the tagged to the untagged species, and we get a single data point on our infrared spectrum. But we get it for all three species at the same time. So then we just scan our laser and we can measure an infrared spectrum of these species at the same time. Now, let me address your question about how fast we can do this. Here's a case of two human milk oligosaccharides, and LNT and LNNT. You see they have very similar cross sections. So we have to put them through 10 cycles on our slim board. The board that we're using to do the separation has a 10-meter single pass path length. So this is about 100-meter path length. So that's why it takes on the order of 800 milliseconds to do the separation here. But then we could measure the infrared spectrum of all of these four species at the same time, because we've put all of them into our trap. We've separated them, but we've put them in these separate compartments of the trap at the same time. And we can then compare them with our database spectra. And we see that the top two are the alpha and beta reducing enantiomers of LNT. And the bottom two, which are peaks 2 and 4, correspond to LNNT. Now, this spectrum took 3 minutes to scan, but you see, we didn't really need to scan quite as far as we have to identify these species, right? If we had taken maybe a fifth of the spectrum, you know, the first 100 wave numbers of this spectrum is clearly distinct enough in all these four species to identify them. So we could have easily measured this in less than a minute. And now this was a particularly tough case because the drift time actually puts a limit on how fast we can go as well, right? Because we can only get 1 point every basically every second, basically. So so that limits how fast we can scan in this particular case.
Mm-hmm.
Now,
is that one scan sufficient for accuracy? You said it's very accurate in terms of how you measure the IR spectrum.
Well, what I mean is we have one cycle, right, would take a second, right? So we would get a second per point. So it's a question of then how many points we want across our spectrum identified. But yeah, we can take, I'll show you just in a minute, we can take a single spectrum without averaging that spectrum to identify the molecule. The signal to noise is good enough to do that. Okay. And let me demonstrate that on, here's a set of metabolite isomers / isobars. These are a series of molecules, all that have a nominal mass of 471. Most of them are isomers, 2 of them are isobars. And we measured using standards their infrared spectra. And here we would take something like a minute to measure each spectrum, because when we measure a database spectrum, you want good enough signal to noise to be able to use it in the future. So these are our database spectra. And then we can say, okay, we only really need these 200 wave numbers of spectrum to distinguish these different molecules. So when we're trying to identify them, we only need to scan this distance. And so let me give you a demonstration of an experiment. So here's a 60-second scan of this particular metabolite isomer. And let me do a real-time scan. This is how long it takes in real time to measure the spectrum. In 7 seconds that you're watching here, that's how long it took us to measure that spectrum. Here's another one, 7-second scan. And you can see how consistent one scan is to the other in terms of identifying this molecule. There's no way we would misidentify the molecule. And now what we're doing is we're developing some tools to automatically assign these spectra. So we take our database spectra. These are multiple copies of our database spectra, and we do a PCA analysis. And here I'm showing the first and second PCA components. You can see some of the groups overlap in this two-dimensional space, but then in higher components, PCA components, they will be separated. So in 2 dimensions, it's a little bit deceiving. But here's the spectrum we measure, and we see that that would put the point right there, which then we can basically automatically assign to this particular species. And we can do this without even any user input, and give some confidence limit in which we determine this particular structure. Now, if we can measure spectra that fast, if we can measure them on the order of 10 seconds, then one could think about incorporating this into standard analytical workflows, even without ion mobility. So, for example, we could take a peak that elutes from a liquid chromatograph, and we can measure a spectrum on the time scale that peak comes out. So this is not a particularly high resolution LC peak, and this is not in real time, but here is a liquid chromatograph peak, and that takes about 20 seconds to elute, 20 seconds across this thing. And during that time, we can take an infrared spectrum, and here's the spectrum we measure. We can compare it to our reference spectrum and clearly positively identify that as sorry, I didn't mean to go forward yet. We can clearly identify that as one of the species in our database. And then finally, one thing I haven't really expressed is we actually have another dimension that we haven't made use of, and that is the mass dimension itself. So in the schematic I showed you of our ion trap, I showed the example of separating 3 isomers that had different ion mobility, how we can measure their spectra simultaneously. But what if we have a whole sample with different masses, and some of those different masses have different isotopes? Because if some of those different masses would overlap with other masses in ion mobility, then in the mass dimension, in the time of flight, we would see those as distinct patterns of tagged and untagged ions. And so we can actually measure the infrared spectra of different masses and different mobilities at the same time. So basically, we could take every mass, we could measure its, separate it by mobility. If there are things that overlap in mobility between them, that doesn't matter because they'll separate in the mass dimension, and then we will get an infrared fingerprint of all these species at the same time. So really, the potential, we haven't quite done this yet, but in principle, we've done everything that suggests that this should work, because we have this other dimension that we're not making use of, and we can fill our trap until we're to the point of space charge limit, and I think we're not quite there yet. So then we can do automatic identification using PCA and clustering, as I described before. So that's what I wanted to tell you about today, and I'd like to just acknowledge the group that I have had the pleasure to work with over the last couple of years. My group is slowly diminishing in number as I'm approaching retirement next summer. So there's only about 5 of us left out of this group here, but people have done most of the work that I've shown you. Stefan Warnke, basically together with Ahmed Ben Faleh, designed the machine, and has really been have been the pioneers of putting these different techniques together. Ali has done the work on the human milk oligosaccharides that I told you about, but all the others have contributed in many different ways. And Priyanka has been involved in developing the collision-induced dissociation techniques. And so we've been generously funded by the Swiss National Science Foundation, the EPFL, and the European Research Council. So that's what I had to say. I hope it will generate some good discussion, and I look forward to your questions.
Thank you, Tom. That was a wonderful talk. Really appreciate you taking the time and giving us idea about what this is all about. And I have a few questions, but let's open it to the rest of the group, see if they have questions, and see any additional questions.
So, hello?
Yeah.
Yeah, Steve Cohen. Oh, I don't know. It was somebody else. Well, okay, Steve Cohen here again. Very lovely talk. It really does open a whole new dimension into mass spec and analysis, etc. One of the questions I have is, how much effort have you put into trying to understand the infrared spectra? I mean, is it worth looking at those peaks there? Beyond a fingerprint.
Yeah. Well, that's a good question. I mean, I spent much of my career doing just that, right? We were working on peptides and for many years, and we've collaborated with theory groups, and we were doing things. We were doing peptides up to about the size of 10 amino acid residues, and it was pretty hard work assigning those. It took a lot of computing power. So for these really complex glycans, I honestly think beyond di or trisaccharides, I think it's pretty hopeless to, at least today, to assign those spectra. And I think the reason is the hydrogen bonding interactions, particularly in glycans, are just hard to get right computationally.
Sure.
But where the calculations, I think, where we are working on calculations are for the smaller molecules. So we're working on smaller metabolites, which, as we've been interacting with different companies and talking to them about their problems, we've learned that, when they have to identify some metabolites which can have 10 different isomers, they have to, and you guys can probably tell me this, right? But they often have to synthesize all these different species, right, to do positive identification. And if by a combination of infrared spectra and calculations, we can narrow that down to one or two possibilities, that saves you an enormous amount of effort, right? So for the smaller species, things I would say roughly on the order of a disaccharide or smaller, that kind of size range, I think there's still hope to get reasonable calculations and identify exactly what the species is, rather than just using it as a fingerprint. Does that, Steve, does that answer your question?
Oh yeah, that does. Thank you.
Steve, where are you from? I'm not sure we've met.
I'm RPI alumni as well, 1980.
Oh, okay. Not so far apart from me. In fact, we were there at the same time. I was 1978, right?
Okay, there we go.
Yeah.
No, I joined Fred McClafferty's group at Cornell.
Oh, okay.
Right after that. So, and then I've eventually made my way over to Rockefeller with Brian Chait.
Okay.
Nice. See, so Tom, I've got another question. Can you elaborate on how you built your database? It seems to me like you need to have standards, but then You alluded to the fact that you can't have every standard made and all that. It's difficulty making standards for every glycan. But can you just, I didn't follow that, how you constructed your database.
So there's two ways we do it. For things for which we can buy standards, we just buy them, right? And we measure the spectra. Okay. But then if you take, so let's say you then measure a spectrum of a glycan and it's not in your database, what do? So we break it apart, and depending upon the particular structure that you've broken apart, there will be certain fragments that are characteristic, that can only be characteristic of that particular isomer, right? And that, I tried to show that in the case of that human milk oligosaccharide. Yeah. And then if for those smaller ones, if we have those in our database, we then can put them back together and say, okay, this is what the parent structure was. And then we put the infrared spectrum of the parent structure in the database. And you don't have to do that process again. Now, then if you go to a still larger glycan, that might fragment into this one that we've just added to our database. And we've done this we've recently published a paper on N-linked glycans, and to show the way we could kind of work our way from smaller to larger by identifying the fragments. You break it down until you identify the fragments, and then you can work your way back up, knowing that a certain fragment had to come from a certain parent. So that's one way that we do it, is by collision-induced association. The other way we've done it is by enzymatic degradation. So let's say we take a glycan, it's not in our database, we don't know what it is. We take some enzyme that we know what that enzyme does to the non-reducing end sugars. Yeah. We cleave it and we measure the spectrum and we see if it's in our database. If it's not in our database, we cleave it again with a different enzyme, and we then see if it's in our database. And then once you get a match, then you work your way back, because you know the specificity of the enzyme, and you can build it up. So we have these two ways that we can build up, both from CID, you go down to you identify, and then you build your way back up, and by enzymatic degradation. The problem is, with CID, with the enzyme degradation, you have better control, right? Because there's more, it's a more specific process. So on the CID, you have to hope that you get fragments that are characteristic of the isomeric structure of the parent.
Mm-hmm. Do you do any sort of linkage analysis with chemical tagging and stuff like that? Because that's also quite kind of challenging, right? To really know the linkage.
Any kind of, what did you say, linkage analysis?
Yeah.
Yeah. So one thing that I didn't mention actually is it was first discovered by Isabelle Compagnon in Lyon, and then we generalized this result that when you make C fragments, the C fragments from glycans, they are themselves intact glycans, and it turns out that they maintain the stereochemistry of the glycosidic bond. So the general wisdom has been, we have to get cross-ring fragments to be able to determine what the linkage orientation is. But in fact, if you get C fragments, then the C fragment carries the memory of the linkage. And if we then have the individual alpha and beta species in our database, then we can identify that linkage. So we published a paper on that, a couple of papers that actually used that approach. But you have to be able to get the C fragments, and sometimes you see abundant C fragments, and other times not.
Tom, I have another question. Do you know or know of David Harvey?
Yes, I don't know him, but I know of his work.
Yeah, because I mean, of course, he's been.
He's at Oxford, right?
He was at. Yeah, I believe he's at Oxford in the UK, and you know, and I guess you know, much of his work has been in
CID of negative. Yeah, CID of negative glycation.
Yeah, elucidating linkages and everything. And I'm, you know, I'd be curious to know what he would think about something like this, because you look, it's another tool. It's another useful tool, and as you know, it's a quagmire glycans. So I mean, I haven't been doing this for years now, but I know the difficulty of this, and it certainly remains. But anyway, I just thought I'd ask.
Yeah, I know he is. I think he's done a little bit of work recently on using ion mobility. I think he's collaborated with some ion mobility groups.
Yep.
And we were in contact with him at one point about you know, the possibility of us trying some of the molecules that he's looked at. But this was during COVID, and we seem to have lost contact actually during that time. So we haven't pursued that with him.
Okay.
But I certainly know of his work.
Okay. Any other questions from the audience? It's been awfully quiet. I guess it was very clear.
Just a small, very quick question about the resolving power that you need for ion mobility. What is the minimum resolving power you need in ion mobility to separate?
Yeah. Well, this depends upon what we're trying to study, right? So, you know, here we were taking problems that were pretty tough from a you know, things that would have very similar cross sections. So, for example, the alpha and beta anomers of some N-link glycan, right? They only differ by a single OH group, and there, you know, we sometimes needed path lengths of, well, the one case I showed when we were separating LNT and LNNT required 100-meter path length. So, you know, this on our slim board, we have a 10-meter single pass on our slim, and we sent it through 10 round trips to do that. And so that's I think that's the best we've done in terms of actually measuring a spectra. We have done, I think, as much as almost a kilometer in terms of just ion mobility, and you know, Dick Smith has done this, right? He's shown that he can get a kilometer path length, and as long as you're within the mass range of that the RF supports on the slim boards, you can get almost completely lossless transmission of these things. So so you know, I think we've gotten over 1,000 resolution on our slim. But you know, if you think about it, it's not. I mean, liquid chromatography has very good resolution, right? The problem is just it's difficult to use it to assign things. So we could actually replace our ion mobility device with a liquid chromatograph, and we could use the same procedures, right? All we need is something to separate the different species, and then we measure their infrared spectra. And it's not like we're using, so we don't use collision cross sections. We don't use the drift time as an identifier, because then you have to really control things very accurately, right? The pressure, the temperature, sometimes you get pressure fluctuations, you know, you get tiny pressure fluctuations on the time scale of several hundred milliseconds, which can give you a little jitter in your arrival time distribution. So we don't use it to identify, we just use it to separate. But we could use a liquid chromatograph to separate and do the same kind of identification kind of thing. We're also pursuing a capillary electrophoresis to separate and then measure infrared spectra. So you know, we have this really nice device that we built, and we built it ourselves, and it works beautifully. But going forward, I think we want to be able to make infrared spectroscopy accessible to many different platforms, both different ion mobility platforms and different separation techniques, because we're convinced that it's, and you guys can tell me, because you're probably using these techniques, but to change the paradigm and convince people to give up their liquid chromatographs and use ion mobility is hard work, right? They're invested, you're invested in this particular technology, and I think it's naive for us to think we can convince people to do that. But if we could make an add-on to a machine so that you go through your normal procedure of LC-MS, but you can at the same time measure an infrared spectrum, I think that would be a much better way to get infrared spectroscopy accepted by the broader community. So that's kind of the strategy we're taking.
I see. Thank you, Tom.
So that was a long answer to a simple question.
No, it was a very good answer, actually. So, and I have one question about the alignment of IR beam with the ions. So how challenging that part is?
It's actually pretty easy. So the ions are confined to a relatively small space. The ion trap dimensions are, it's probably 4 or 5 millimeters square is the ion trap. And the laser beam largely fills that whole volume. So these, the particular laser that we use, it's a fiber pumped solid state laser, which just gets gobs of laser power. I mean, so we can blow the beam up and fill the trap, and we still have to be careful about saturating the transitions. So we could do it with much less laser power than that, and still measure good spectra. So it's really, so there's really not much alignment problem there.
That's great then. So thank you, Tom.
Yeah, Tom, I have a follow-up question on the, it's quite an engineering feat to kind of come up with a cryogenic trap 40 Kelvin, and how challenging was it to develop and design something like that? I was at Purdue when Tim Zwier and Scott McCluskey was building an instrument similar to what you described, but it seemed like there's a lot of work that went into it, and soldering certain things to maintain huge temperature differentials, vacuum, all that is very critical at those temperatures. Are those the same problems that you faced, or is it different?
Yeah. Well, first of all, we actually helped Tim build that trap in Purdue. So Tim is a good friend of mine. He's been a good friend for years, and we helped him to develop that trap. He actually sent it to us for one point, and one of my guys helped rebuild it for him. And we've actually moved away from these multipole traps because they're pretty finicky and difficult to align, and we've moved to these PC board traps. So here's the picture of the trap. It's basically 2 PC boards, and these things are then there's a copper block that they're pressed against to cool them. But we started probably around 2014 or 2015 developing these PC board traps, and they are infinitely easier to align and to cool than these multipole traps. So I'll never go back to using a multipole trap. And if you want to change the design of this trap, you just go reprint the board, and you can change the layout of your electrodes. And because you make this into a sandwich, there's really no alignment problems. It just everything kind of fits together, and you bolt it together. And so this is a lot easier technology than what Tim and Scott were doing.
Okay. One more quick question is, are there any more questions from the audience? I just want to make sure that nobody skipped away from questions. No, okay. So I guess I have one last question. I think we'll end this discussion with this. So you mentioned that alluded to like not having LC separations at all. If we can manage with ion mobility with some very front end rapid introduction of samples, to improve throughput, with your very long drift separations and multi-pass, almost I would say 100 meters, right?
Mhm.
Do you think you can couple this for something like a rapid fire where you're rapidly introducing samples like every 5, 6, up to 10, 20 seconds?
Yeah, well, it really depends on the kind of sample. But, as I showed you, we were measuring spectra in 7 to 10 seconds, right?
Yeah.
So, okay, maybe every 5 seconds would be a little bit fast.
Let's say 10 to 20 seconds. Do you think this device can resolve isomers and then get an IR spectrum?
Yeah, I don't see why not, right? The only thing is, depending upon how close the isomers are, so part of our time scale depends upon how long it takes for one cycle to do the separation, right? And if the separation takes too long, then because our laser is continuous, it's a CW laser. So we're not limited by the rep rate of the laser. So we're limited by the cycle time of the ions on the board. So if you separate them in 20 milliseconds, then you can go much, much faster than if you separate them in 200 or 800 milliseconds.
Yeah. So I was thinking from a pharmaceutical standpoint, we might not, like for example, some of our release glycan work that we're doing, we take quite a bit of time separating them by LC, like Helic or some kind of liquid phase separation technology. Whether we could just go with ion mobility alone to do the same thing, but have a way to do flow injection or some very rapid way of introducing samples to make use of ion mobility separations. And
so you're saying not separate them at all by liquid chromatography,
or limited separation. Let's say kind of a solid phase extraction or very limited short LC separations, like less than a minute or so.
But would you collect fractions, or you would just put the whole thing right into your machine?
Whole thing right into the machine,
yeah. Well, then there's a question of peak capacity, right, of your ion mobility. I think that is probably the big advantage of SLIM, right? Is that you have you compare SLIM probably to TIMS or to water cyclic, right? Water cyclic has only about a meter path length, so it has a pretty small peak capacity. The nice thing about SLIM is you can have in 10 meters on our board, or Mobile Ions has 13 meters. You can put a lot of peaks in there, and it's okay if mobility and for us, if you're trying to do only mobility separation, then you have a little more of a problem. But we have this extra dimension of mass, right? So if you separate by mobility, but you have masses on top of each other, and we can measure the infrared spectra of those at the same time. It's all contained in the time of flight. I guess from the point of view of ion mobility, you can do the same thing, right? Yeah. That you have you can separate the mass and the mobility, but you see, we can measure the spectra of all those guys at the same time. Yeah. So we haven't tried a super complex sample like that to see how much multiplexing we could do, but it would be an interesting challenge to do that.
No, I see the value of extra dimensions that you pointed out with having mass information coupled with IR spectrum to kind of distinguish things that adds additional benefits, doing things that you have very limited separation with drift separation. So these are all interesting technologies. I think shows the power of the various the high dimensionality to your work, and how you bring in new capabilities to to very complicated analysis. So thank you. So I guess if we don't have any further questions, let us thank Tom once again for a wonderful talk. And if you don't have anything else, let's end this meeting. Thank you again, Tom, for taking this.
Okay, well, thanks for having me. It was really a pleasure.
Yeah, thank you. Bye-bye.
Thank you,
All right.
Tom. Thank you, Harsha, for organizing. And I'm
Thank
also from Purdue University, I just noticed.
Yeah. Oh, you are? Okay.
Yeah.
Where were you at Purdue?
I just graduated in August.
Okay. For whose group was he? Were you in?
I was working with Julia Laskin in collaboration with Graham Cooks.
Oh, yeah. I think I've met you. That's why I thought a very familiar face. I visited Purdue like in 2019 where you had that workshop, industry workshop. I think you gave a demo on one of the systems there. I think the soft landing, or I can't remember.
Right. Oh, yeah. I'm working in soft landing, yeah.
Okay, good.
I remember now. Very nice to meeting you. It was great talk, Tom. Thank you very much.
Yeah, sure thing, Habib. Thanks, Tom.
So yeah, let's keep in touch, Harsha. Huh?
Yeah, for sure thing. Very interested now that I know that your business is like a CRO, and there may be ways we can see how this works with some of our internal work. Yeah.
Okay, so yeah, don't hesitate to get in touch if you have interesting problems for us. So
yeah, absolutely. And I'm also interested to know what your thoughts were with droplet chemistry. I think at some point.
Yeah, I'm not so sure. Like I told you, we had a master's student on it, and I think that's a rough way to go. I'm not sure we're gonna in my research lab we can mess around with that stuff, but once I retire and all of our stuff goes into the company, I'm just not sure we're gonna have the time to mess with that stuff.
Yeah, it's more of academic interest right now.
Yeah.
You don't see too many, industry people interested in that approach.
Yeah.
At least I have struggled trying to convince my colleagues to do that. Although we proved it works very well, and you don't have to spend any time doing in solution dilution, they still prefer doing it that
way. Yeah. So
nice. Thanks.
All right. Thanks, Harsha. All right. Bye.
Bye.
Bye, Habib. And Brett, I hope to meet you sometime.
Thank you, Tom. Yeah, same here. Great talk. It's great to hear this discussion.
Thanks.
All right.
Yeah.
Thank you. Bye-bye all.
Thanks. Take care.